up to this point right now, you have mainly been looking at Stuve diagrams for temperature, and then in the last exercise we introduced dew point. Well, I'm going to introduce two more things on a Stuve diagram today, and these two things actually are going to make your life a lot easier than you would think. And so these two things are actually called adiabats, and they deal with what's called adiabatic cooling. As air rises, it cools adiabatically, which means it only cools due to expansion or contraction. So as air rises, it expands and cools. As air sinks, it compresses and warms. And there's actually a set rate with which this happens. If you've ever taken me for the Met 10 lecture class, I've actually had you calculate these by hand using equations, or I've had you draw diagrams. The good news is you're not going to do that right here. Instead, I'm going to show you the tools that a Stuve diagram gives you to do it. And so before you decide to go drop the class or anything, I'm going to promise you this is actually a lot easier. And actually, for those of you who are taking my online lecture class, you've probably already done this. So here's how it works. There are two sets of lines on here. Let me pull up my laser pointer. There are two sets of lines here. The first set of lines are these dashed blue lines. These dashed blue lines are what are called moist adiabats. So what happens is as air rises and expands and cools, eventually it can cool to the dew point. Once it cools to the dew point, you're going to get cloud formation. Now clouds form via condensation. And when condensation occurs, it releases latent heat into that air, which slows down its rate of cooling. And so moist air cools at a rate of 6 degrees Celsius per every 1,000 meters. Again, I'm not going to make you calculate what the temperature is at different heights because these lines actually do that for you already. Now, before air becomes moist, becomes saturated, it actually cools at a different rate called the dry adiabatic collapse rate. And we can actually follow that using these green lines called dry adiabats. So these are called dry adiabats, these solid green lines. And these actually represent a rate of cooling 9.8 degrees Celsius per every 1,000 meters. And if you've heard from my online class or from my on-campus class, I've said 10 before. I usually round to 10 there because it just makes the numbers easier to work with, but a more precise rate is 9.8. Okay, so here's how we do it. If I wanted to calculate the temperature of a parcel of air at any given height, what I'm going to do is start at the surface. So start down here at the surface, and then if the parcel is saturated, I'm going to follow a dashed blue line representing a moist adiabat. And what I'll do is I'll start at the surface and I'll travel up that line until I've reached my desired height. So for example, let's say I have a saturated parcel of air, 17 degrees Celsius at the surface, so it's right down here, conveniently located right on a moist adiabat. And let's say I want to know the temperature of the air at 300 millibars. Well, I start down here, and I simply just follow the line, making sure I'm on the same line, all the way up to 300 millibars. And my temperature would be right around 55, 56 degrees Celsius. And that's it. Done. The same is true for dry adiabats. It just now, instead of following the dashed blue line, I'm instead going to follow the solid green line. But the same thing, if I wanted to find out what the temperature at 300 millibars was, again, start at the surface, and then travel up until I reach 300 millibars. And so dry adiabatically, I would get a temperature of closer to negative 68, 69 degrees Celsius. And so this kind of does bring an interesting conclusion. At 300 millibars, a moist parcel is around 45 degrees Celsius, and a dry parcel is around 68 degrees Celsius, negative 68 degrees Celsius. And that's just because dry air cools faster than moist air because of the whole lack of latent heat release. So that's what's happening here. Now, with that said, what would happen if we started with a parcel of air at the surface, it rose and cooled dry adiabatically, but then it cooled to the dew point at some point? It actually became saturated. Well, what actually happens is, if that occurs, basically all you would do is just like, let's say you're on a freeway and you want to change over to another freeway. If you start on a dry adiabat, you would then switch over to a moist adiabat. And here's an example right here. So suppose you have a parcel of air that's dry at the surface, and it has a temperature of 28 degrees Celsius. You would follow up the dry adiabat from the surface, 28 degrees, you'd follow it up until that height that it becomes saturated. And here I say, okay, it becomes saturated at 900 millibars. And then all I would do, follow it up until I wanted to get to my desired height. In this case, let's say my desired height's 500 millibars. So I would just follow it up until I reach 500 millibars. Let's do another example. Let me pull out my pen here. And just to make this a little more interesting, let me use red to represent dry. Let's say we have a parcel of air with a surface temperature of, let's do, sorry, sometimes this cursor disappears on me. Let's do 8 degrees Celsius, like right here. And oh, and by the way, if you ever reach a point where your temperature is not directly on a line, draw a line that is parallel to the two closest lines, to the two closest dry adiabats for dry air, moist adiabats for moist air. But the textbook actually does a really good job of keeping you directly on one of these lines. That's more if you get bored and you want to do it yourself. Okay, so back to what I was saying though. Let's start at the surface, and then let's go up, sorry for my wiggling. And let's say the parcel becomes saturated at 700 millibars. So it's rising up, rising up, rising up, and then it reaches 700 millibars. Now what happens here, once it reaches 700 millibars, and I'm just saying, so let's let it rise, and then it's gonna hit 700 millibars and become saturated then. Once it becomes saturated, all that I do is I now switch lines. I go from the dry adiabat line over to the moist adiabat line. So all I've done is I've switched. And then let's go up until, let's say, 300 millibars. So I follow it up to a height of 300 millibars. And there we go. And that would be my temperature. That would be the temperature of the parcel of air up at that particular height, up at 300 millibars. So that's really all that you're going to do for this exercise. One of the questions that they do ask you is, what happens when a parcel of air sinks back down? Well, one of the things that happens is when moisture condenses outside of a parcel, or once moisture condenses, it is no longer a part of the parcel. It is gone. Therefore, the dew point continues to decline, decline, decline. Eventually, what happens is if a parcel begins to sink, it sinks automatically unsaturated. So, if I were to somehow take this same parcel and drop it back down to the surface, I would want to follow the nearest dry adiabat. It looks something like this. Now I'm following the nearest dry adiabat, drawing a line parallel to it, and continuing down. Voila. Now if you notice there, what actually happens is the air is now warmer at the surface than it was initially. That's because once the air became saturated, condensation happened, releasing heat into the parcel. That heat didn't leave, but that water did. The condensation did leave. And so that's what's happening here. And actually, this is a very, if you ever heard of the rain shadow effect, this is actually very important for the rain shadow effect. As air rises up one side of a mountain, it becomes saturated quickly, rains out, and then once that air travels over the other side of the mountain, it warms back up, dry adiabatically. By the time it reaches the surface of the earth, it is much warmer than it originally was.